Let me know if there are any technical problems. This is where we left off about a week ago. We had just talked about semaphores, and I was kind of hurrying through this material. I'll remind you of it real quickly. We had just finished kind of solving some toy problems with semaphores, ones that were like this, and we'd code up our own solutions and talk about that a little bit. And then we were going to try our first real problem, one that you might actually have to use in a multi-threaded program. And it's what's called a classic synchronization problem. It's one that typically everyone learns in operating systems class. It's kind of like, and someone mentioned this when we were talking about it, it's kind of like implementing your own pipe. You want really an array of items. They can be of any type you want. They could be bytes or some other struct. It's got limited capacity, and you want one or more threads to be able to put items in one end of that array, of that buffer, and you want a consumer or one or more consumer threads to be able to get items out of it. And we were going to implement our own efficient version of this using semaphores. We already saw this representation. We're going to implement it as a circular queue. And like it showed, well, we got an array that has one item for everything that can fit in our buffer. And we're going to use a first index to keep up with the first item in the buffer. So whenever a consumer comes to get one out, that'll be the next one they get. So first we'll move ahead as we take items out of it. And as we put items in the buffer, num will move ahead, keeping up with how many items are in the buffer. And we already came up with our first solution to this. The word solution in quotes up there at the top should make you a little nervous about this. One problem is it doesn't use the thing we just learned about. It doesn't use semaphores. So we're going to fix this by making it use semaphores, making it much more efficient. Just to remind you of how it works real quickly. Remember, for the bounded buffer producer consumer problem, if the buffer is full, then the producer has to wait. If the buffer is empty, then the consumer has to wait. So we're pretending this is producer code over here. A producer makes an item, and then if the buffer's full, they ride around in this while loop until there's available space in it. And then they put their item in the buffer, moving, when we put an item in the buffer, num moves ahead. So increasing num because there's one more item in the buffer. Similarly, when the consumer wants to take one out, if the buffer's empty, we have to wait. And then once there is something in the buffer, we get the next item out. We advance first to the next item, wrapping around. That's what this mod is doing, since we're doing a circular queue. And since we just took an item out, num is one smaller. And then whatever the consumer needs to do with that item, we'll pretend this function does that. And I know it's probably the last thing I did a week ago when we were talking about this. I pointed out that this solution has really two problems. One is it depends on busy waiting. So if the buffer is full and a producer is ready to put something in it, the producer will just sit in this while loop, burning up CPU time as fast as it can. So that's really inefficient, especially if everyone feels like it's okay to do that. And we pointed out, well, there are some race conditions also. This num plus plus, if it happened at about the same time as this num minus minus over here, and that could happen if your buffer was partially full, then we have already seen that was kind of the first thing we saw that can cause race conditions. So we're going to fix this by adding semaphores, and the first thing we're going to do is fix the busy waiting. We need to make the producer block, at least we need to use a semaphore to make them wait when the buffer is full. And we're going to count on the OS implementing semaphores efficiently. So if a thread has to wait, it'll block rather than wasting CPU time. So that's what this empty count is for. You can think of that as counting the empty spaces in the buffer. And every time we put an item in the buffer, that empty count goes down. In fact, that's what this acquire is doing right here. Remember, you can think of acquire as blocking a thread if it tries to acquire on a semaphore that's 0 or negative. But you can also think of it as maintaining a count. And here we're definitely going to use that count. Whenever we acquire on this empty count, it starts out at the buffer size, so we'll say that's 10. Every time we acquire on it, it gets decremented by 1. And when it hits 0, we don't even get past this acquire. The producer is going to block here until, we'll see in a moment, until the consumer thread takes an item out of the buffer. So if acquire is implemented efficiently, this will keep counting down until the number of empty spaces in the buffer hits 0, and then it'll start blocking the the producer thread. And then we're going to do the same thing over here. It's kind of weird that I need 2 semaphores to do this. They're kind of doing the same thing, but I'm using them differently. Empty count, you can think of as counting empty spaces in the buffer, and every time we put an item in it, we decrement that, we acquire on that semaphore. Full count is counting filled spaces in the buffer. And every time we take an item out of the buffer, we decrement that so that if there are no full spaces, the consumer blocks. And that's what's going on right here. Full count starts out at 0. We're pretending the buffer is initially empty. Let's say there are some items that get put in it before this thread starts running, just to make it easier to talk about. Every time this thread doesn't acquire, it's going to decrement that count, the number of full items, until that count hits 0. And then this acquire is going to start blocking the consumer thread. And again, we're counting on that being done efficiently, probably with help from the OS. So I've focused on these 2 acquires up here, the cases where we're decrementing these semaphores, where we might want to block a thread. When do we increment those? Well, those are the 2 operations done down here at the bottom. For the producer, once it has put an item in the buffer, it does a release on full count, and that increments it. If we just put an item in the buffer, there's 1 more item there, so that would let 1 more consumer get past this acquire. Same thing's going on over here. Every time the consumer takes an item out of the buffer, we're releasing on empty count. So we just made a new empty space by taking a thing out of the buffer. And when we release on that, if there was a producer waiting to put an item in the buffer, that wakes up 1 of them out of this acquire and lets them put the next item in the buffer. So a nice thing about this solution, and I've kind of hinted at this by what I was saying, is this would work even if you had multiple producer and consumer threads. There's one more thing we have to fix, and that's the question mark down here. Before we move on, any questions about this? So we're using 2 semaphores, 1 to efficiently block the producer when the buffer's full, and 1 to efficiently block the consumer when the buffer's empty. There's still one problem, and it's the same one I hinted at before. It's this num plus plus and this num minus minus over here, and this code where we're putting something in the buffer. It's possible, even if you only had 1 producer and 1 consumer thread, it's still possible that 1 thread could be putting an item in the buffer, and at about the same time, another thread could be taking an item out of the buffer. And that means these 2 lines of code could execute at the same time. And we already saw that that's a race condition. It could leave it in an unknown state. So we need to fix that. The only thing we need to do, though, is we need to put mutual exclusion code around this. If a producer is in the middle of putting an item in the buffer, we don't want any other producers to be messing with the buffer, nor do we want consumers to be messing with it. Same thing over here. If a consumer is in the middle of taking an item out of the buffer, we don't want anyone else messing with that buffer. So we'll fix this by adding 1 more semaphore. And it's really the first thing we ever did with semaphores. It's for providing mutual exclusion. So that's what these 2 blue lines of code are. Before the producer starts putting an item in the buffer, it'll lock everyone else out. And before a consumer starts getting an item out of the buffer, it'll lock everyone else out. So only 1 thread at a time should be able to be in either this code over here or this code over here. That semaphore I'm just using for mutual exclusion. So I did what we've always done. I wrapped acquire and release around the code that needed to be mutually exclusive. And I set that semaphore's initial value to 1. And I think this fixes it. I'll mention, I've seen students get these 2 lines backward. That's probably worth thinking about, but I would say you don't want to be acquiring on this lock before you make sure there's space in the buffer. Same thing over here, you don't want to be locking everyone else out before you make sure there's something in the buffer. So just be careful about that. Hopefully the ordering of this code makes sense. And I try to make it easy to remember. So here, for me, if I need to remember this solution, the semaphore-based solution here, I feel like I usually just have to remember what the semaphores are doing. If I can remember the job of each semaphore, then I can usually write the code just by thinking about that. So just to remind you what we just did, and hopefully to give you a hint at remembering this, we used 3 semaphores. Lock was the last one we added, but it's probably the simplest to think about. That's just for providing mutual exclusion while we're in the middle of manipulating the buffer, either adding an item or removing it. We just wrap acquire release around the manipulation of the buffer, and we set that semaphore starting out at 1. And then I think the trickier 2 semaphores, these are the ones that are really using the integer value stored in a semaphore. We've got 1 semaphore full count for counting the number of filled spaces in the buffer. It starts out at 0, and every time the consumer is about to get an item out of the buffer, it acquires on that because it needs kind of to take the next filled item. We had another semaphore that's, I mean, its job is kind of redundant. It's also counting how much of the buffer is full, but to get the blocking behavior we need both of these semaphores. So we've got an empty count. You can think of it as counting the number of available spaces in the buffer. It starts out at whatever the buffer capacity is, and the producer acquires on it, decrements it every time they're about to put something in the buffer. I pointed out, here we're really using that counting behavior maintained by a semaphore. I'll back up and show you this on this one. Imagine a producer comes along and puts a bunch of items in the buffer. Every time they do a release on this full count, every time they do a release on this semaphore, it increments its count. So if we put 5 items in the buffer, that's 5 consumers. The semaphore gets incremented 5 times. So that's 5 consumers that get to go past this acquire without blocking. So the fact that semaphores maintain a count, I think, is often pretty handy when you're trying to use them for a solution. Their count kind of remembers how many times release has been called on that semaphore. We've been using semaphores so far as if the OS is going to provide these for us. And in practice, it is. In practice, a modern OS provides efficient semaphores. But in this class, we also try to look at things from the other side. We saw that if you don't have any special help, it can be awfully hard to even write plain old mutual exclusion code. It took us a while to figure out Peterson's algorithm when we were first trying to solve the critical section problem. And then we realized that on a modern processor, that solution probably isn't even going to work. So designers of an operating system have to be able to solve problems like this on their own. If you expect your operating system to provide semaphores for you, you've got to figure out how to build something like a semaphore inside the operating system. So we're going to take a little side trip here to talk about how you would do this. We'll start by just trying to do what we originally tried to do. We're going to try just to build a solution to the critical section problem, just to build something that provides mostly mutual exclusion. One way you could do this is if you didn't have a multi-core system, if you only had 1 core, then only 1 process or 1 thread could be running at a time, which means you don't have to worry. Well, I want to say you don't have to worry as much about race conditions. A better way to say that might be you could try to do some things that would help prevent race conditions. If you're on a uniprocessor and you're in the middle of some critical section code, the only thing that could let another thread run at the same time is if the OS context switches to that other thread and lets it have a turn on the CPU. So if we could just prevent that even for a moment, then we could prevent race conditions, at least in a critical section. And some systems would let you do this. Some systems let you temporarily disable interrupts. You can say to the CPU, I'm about to do something critical. Don't interrupt me until I tell you it's okay. And then as long as you had interrupts disabled, the OS could not context switch away from your thread or your process. So you wouldn't have to worry about other threads seeming to run at the same time or their execution getting interleaved with yours. I'll mention if we let a modern system do this, well, we would call that cooperative multitasking. because other threads only get a chance to run when the previously running thread says it's okay, when it enables interrupts. And if we did that, we would be giving up on CPU protection. Remember, CPU protection was that idea that if one processor thread is running on the CPU, we can't let it run forever. It's got to eventually, the OS has to get a chance to run. But if processes could disable interrupts, we would, a bad process could just leave them disabled and the OS would never get a chance to run. So on a modern system, it's probably not going to be a uniprocessor, so we can't depend on that. And if you want CPU protection, you can't depend on being able to temporarily disable interrupts. So what else do we have? Well, modern CPUs, I mentioned that they do some clever reordering of accesses to memory, and that's kind of what broke Peterson's algorithm. But at the same time, when they broke Peterson's algorithm, they gave us something back. They gave us typically one or more specialized instructions that are made for writing synchronization code. I want to talk about a couple of these. We'll spend a little more time on this first one. Modern CPUs will often have an atomic test and set instruction. Atomic here means while that instruction is in the middle of executing, no other CPU instruction run on any of your cores can affect the same memory it's trying to access. So atomic means it looks like it happens all at once. And even if internally, even if it takes multiple steps, the CPUs are built with hardware to make sure that it still looks atomic. So what does an atomic test instruction do? That's what I put in the blue box up at the top of my slides. It does two things, but it does them atomically. So by that I mean, it's as if they both happen at once. You give it a memory location, and it tests that memory location to see if it's 0 or not. In your assembly language class, which most of you are taking right now, you're learning about machine instructions, and you're learning about things usually that are called status codes. After you do a test instruction, they let you do a branch or a conditional jump based on how that test went. And that's the same thing I'm talking about here. This will set a condition code it'll look at a memory location, and then it'll remember whether it's 0 or not by setting one of these condition codes. But at the same time, atomically, it will set that location to non-zero. So it remembers whether it was 0 or not, and it sets it to 1, we'll say. If you had an atomic instruction like this, you could write some entry code for the critical section problem using two instructions like I've shown down here. I've got some slides that try to illustrate how this works, so we'll talk about that in a moment. But this is just like what we were talking about when we were trying to solve the critical section problem ourselves. You'll do a test and set on that memory location. If it was non-zero, you'll jump back and do the test and set again. So at least this little block, these two instructions here, are doing busy waiting. This is often called a spin lock, especially when it shows up as part of the operating system. It's a tiny little piece of mutual exclusion code that locks every other thread out by just looping over and over as fast as it can, testing that same memory location over and over until it catches it having a value of 0. I admit, it has busy waiting, but I'll go ahead and say we are probably going to have to tolerate a little bit of busy waiting inside the OS. We want to be able to believe that it's not very much, or that if you're in the middle of a loop like this, a spin lock that's doing busy waiting, you have some guarantees that you're not going to spend very much time there. You'll just be there for a moment. And I'll try to convince you of that a little bit later. So let me finish trying to tell you how this instruction works, and I've got some slides that try to show it. Let me back up and say, normally, the lock starts out at 0. And you can think of that as meaning the critical section is unoccupied. There are no threads that have acquired the lock. None of them are running in the critical section. So let's say the lock is 1. So that would mean there is some thread in the critical section. What are these two instructions going to do? Well, I already said they're a test and set instruction. So atomically, they look at lock and they remember if it's 0 or not. Here I'm pretending I've got a 0 flag and I set it to false because it wasn't 0. And they set it to 1. Well, it was already 1, so it doesn't change. And then after I've done the atomic test and set, I check to remember if it's 0 or not. In this case, it wasn't. And I set it to 1. After I do that, I do a branch if non-zero. Well, in this case, it was non-zero, so somebody already had the lock. And like my arrow over here tries to show, that takes us back to the test and set instruction. And as long as this lock has a 1 in it, we're just going to keep doing that over and over and over again. What if the lock was 0? So backing up, before we were pretending it was 1 and we talked about what would happen. What if the lock is 0? Well, that means no one's in the critical section. So our atomic test and set instruction tests that lock, remembers, oh, it was 0. So I set this flag to true, pretending like I'm remembering, oh, it was previously a 0, but I also set it to 1. So that's the important part about the atomic test and set. It remembers whenever anyone was in the critical section by remembering whether this memory location had a 0 or not in it. And simultaneously, it locks everyone else out. So I got past the branch if non-zero. Lock is set to 1. I can hang out in the critical section for as long as I want. And then when I'm done, I set lock back to 0. And that lets the next thread into the critical section if it wants. On one of your exercises, you get to use an instruction like this. It's not really a machine instruction, at least not directly, but there is support to use what look like atomic instructions, even in a language like C. So you will, in an exercise or two, you will get to write some code like this yourself. Questions about the atomic test and set and how you could at least use that to provide mutual exclusion? I'm going to pretend that we can use this kind of code wherever we want inside the operating system. So remember back here, I called this thing a spin lock. Later, we're going to pretend we can just put spin lock code in wherever we need to at least, with some busy waiting, to at least get mutual exclusion when we need to inside the OS. I mentioned there are a few different instructions that are used to provide mutual exclusion. Test and set was the one that we spent the most time on, but you can also do this with an atomic compare and swap. It's a little more complicated, or the instruction itself does a little bit more. You can see this blue box up here that shows what it does is a little bit bigger, but the way we're going to use it is a lot like what we just did, so I'll try to describe this more quickly. The atomic compare and swap instruction takes a target memory location. So you're saying, look at this memory location. I expect it to have this value in it. And I want you to put this new value in it. And if you look at this pseudocode for what it does, you can see it says pretty much what I just said. The atomic compare and swap looks at the target memory location, and if it has the value you expected, it sets it to the new value you want, and it remembers that it has the value that you expected. I may have, when I was pointing at this instruction, I may have read that, or I may have said that a little bit wrong. So I'll say it again real fast. It looks at the target location, and if it's the value you expected, it remembers, it sets one of the condition codes to true, remembering that that location had the value you expected. I set that location to whatever new value you gave me. Otherwise, if it didn't have the value you expect, I set the condition codes to false and leave everything unchanged. And like I said, we're going to use this a lot like we just did the test and set. I'm going to have a shared variable lock. If it's 0, that means no one's in the critical section. If it's 1, that means someone else is in the critical section. When I want to get into the critical section, I'll use this atomic instruction to say, look at lock. If it's got a value of 0, replace that 0 with a 1 and remember that it had a value of 0. Remember that it had the value you expected. The next thing I do is I check the condition codes, and if it didn't have the value I expected, if the condition code wasn't true, I do the same thing we did before. I go back and just redo this instruction over and over again. So the only way I get past this line is if lock had a value of 0 in it. And when it does, I set it to 1. So that locks everyone else out of the critical section. Same as before, on my way out of the critical section, I set lock back to 0, and that lets someone else in the critical section if they want to. Questions? All right, I hope people are there. Our job is to try to write a semaphore. And this is enough. We'll pretend we can have either of these instructions and that we can write spin lock code. And that is enough to let us build our own semaphore inside the OS, and one that would actually work. It's not a very efficient one. We're going to fix it in a moment. But for now, all we need is spin lock code. If I had to, so I'll try to talk you, this is sort of pseudocode for how you could implement acquire and release so that they actually worked if you had to implement them inside the OS. Let's do release first, because it's easy. I'm going to pretend my semaphore just maintains an integer count. So you can see inside release, the interesting piece of code is I just increment that count. But I protect that with this spin lock entry and exit code. So up here, I'll pretend this is that test set instruction and branch if non-zero. And down here, this is just setting that flag back to 0. So this, with some busy waiting, this will lock everyone else out while I'm in the middle of incrementing this semaphore. And that's good, because otherwise we might have a race condition. So all release does is, with mutual exclusion, it increments the value of the semaphore. What does acquire do? Well, I think of this as checking the value of the semaphore over and over and over again until it has a positive value. And when it has a positive value, we're going to go ahead and decrement it. So inside this while loop, this is that over and over again, I said. Over and over again, at least until we set this flag to true, I'm going to lock everyone else out using the spin lock code. I'm going to check the value of the semaphore. And then if it's positive, I'm going to decrement it and remember that I decremented it. Since this is all inside mutual exclusion code, I don't have to worry about any other threads messing with the value of this semaphore before I set this flag, or really, I guess, messing with it between when I look at it and when I decrement it. The spin lock code locks everyone else out. And if I successfully decrement it, I remember, oh, you successfully acquired on it. And that gets you out of this loop. So this proceed flag starts out at false. And then I keep doing this over and over and over again until I successfully decrement it, and then that gets me out of this while loop. This is inefficient, and it's got busy waiting code. I can pick 3 different places where it has it. The spin lock entry code is hiding some busy waiting, because we just talked about how that works. Same for this code over here. And this while loop, I mean, it's an outer loop, but it's also looping over and over again until it successfully decrements the semaphore. And that part could take a lot of time, because if the semaphore has a value of 0, you're waiting on some other thread to release on it, and who knows how long that could take. So a thread could spend really an arbitrary amount of time riding around this while loop, this outer loop here. And that's what we're going to fix next. We're not going to be able to make the other busy waiting go away. In practice, that's often how you have to increment semaphores. But we want to make sure that if you can't acquire on a semaphore, instead of just checking over and over again, your process will block. It will efficiently start waiting, and then the OS can go run someone else, some other thread, until someone releases on that semaphore. To do this, and I've said this a couple of times already, we're going to need help from the OS. So if we want semaphores that work efficiently, we need the OS to be able to block us when we can't make progress. So we're going to count on this being implemented inside the OS, at least partially. And the way we're going to block threads when they can't make progress is we're going to have a little queue of process control blocks associated with every semaphore. Just like we have queues for other things. We said the disk has a queue of processes waiting to use it. The network card might have a queue of processes waiting to send out packets over the network. A semaphore might have multiple threads blocking, waiting to acquire that semaphore. So to make it efficient to let them block, we're going to have a little queue of waiting threads or waiting processes associated with that semaphore. If you try to acquire on the semaphore and you can't acquire on it yet because it has a value of 0 or negative, we're going to put you on that queue and mark you as blocked until someone else comes along and releases on that semaphore. And with a queue like this, we can finally have an efficient implementation of a semaphore. Here's what it might look like. I'm pretending that I've got a couple of calls I can make. I'm pretending that so we're pretending this is code inside the OS. And whenever we call block, that marks the current process as blocked. It puts it in, it marks it as being in the waiting state. And we'll see later, we're also going to put it on that queue when we do that. And wake up will mark a process as runnable again. It'll put it in the ready state, and it'll put it back on the ready queue. So it'll then wait in the ready queue. It'll sit in the ready queue until it gets its turn to run. So this is pseudocode for both of those operations, pseudocode that would actually work. I'm going to try and talk through this real fast. Let's do acquire first on this case. So the first thing I do is acquire a spin lock. So I lock everyone else out. So until I release that, I don't have to worry about anyone else messing with the data structures I'm messing with. And then I kind of do what our previous solution does. I look at the value of the semaphore. We'll take the easy path first. And if it is positive, that's the else case down here, I decrement it, and then I'm done. I release the spin lock. So you successfully acquired. But here's where we're going to be smarter. If you look at the value of the semaphore and it's not positive, well, you can't make progress, but instead of just busy waiting, we're going to put you on that queue. I'm going to put the current process on here. I'm pretending that s.list is the name of the queue of processes associated with the semaphore. So I'll queue you up on that process, or sorry, on that queue of processes. I'll mark you as blocked. Now what do? Well, I can't keep running the process I was running, but I'm the OS. I've got to pick something to do with the CPU next. And that's a good job for the CPU scheduler. So if the process that was just running blocked in an acquire, we'll go pick another process to run. So at this point, we don't return to the process that was running here. At least not right now. We take whatever CPU we're running on and let someone else have a turn on it. All right, let's do release now. So same as before, at the top of release, I lock everyone else out. When I'm done, I let them back in. So now no one else can be messing with the semaphore while I'm messing with it. I look at the value of the semaphore. And if it's 0 or positive, well, here's my thinking on that. That means if there was someone waiting on the semaphore, I might be able to wake them up. So if the value was 0 or positive, and that queue of processes is non-zero in length, and there's someone waiting on the semaphore, I'm not even going to increment it. I'm just going to pretend that I incremented it and the other process decremented it. So I'll just remove that process from the queue. I'll mark it as runnable, and then it will resume running from here, at least from inside the CPU scheduler call, as if it had just successfully decremented the semaphore. We just didn't go through the steps of actually incrementing it and then letting the other thread decrement it. We just pretended we did that. If the value either wasn't 0 or positive or no one was waiting on it, I just increment the semaphore and then we're done. So this, it's pseudocode, but it shows that as long as we could write a spin lock, using stuff that we've already talked about would give us an efficient way of building a semaphore in the operating system. It's still got some busy waiting, and I said it would. If I had to point to it, I would say it's right here and right here. That spin lock entry code still has some busy waiting in it, but I shouldn't have to wait there for very long. If I'm in this entry code and I can't acquire the spin lock, because someone else is over here, say running in release, Well, there's no looping in release. So if they're running in the release code, at worst, I'm going to sit in this spin lock until they've checked this condition, they've dequeued a process from the queue, and they've woken it up. Or they check this condition and then they incremented it. And as long as it's just a sequence of a few instructions that I have to wait for, I shouldn't spend very much time in this entry code. It doesn't depend on how long a process might wait in acquire. It depends only on how long it takes for a process to finish running this little block of code. Questions. So I claim we just talked about how you could feasibly build a working semaphore inside the OS. And that's what we're going to count on using from here on out. There are really two kinds of semaphores, and I've hinted at this a little bit, although I haven't really said it. I talked about how, especially for our bounded buffer producer consumer problem, the count maintained by the semaphore is awfully handy. We use that to count empty and full spaces in our buffer. But that's not the only kind of count of semaphores there are. The ones we've been pretending we have, you would normally call those counting semaphores. The semaphore always maintains an integer count. There are also semaphores called binary semaphores that still offer the same operations, acquire and release. They just don't really maintain a count, or said differently, their count is always either 0 or 1. If we had a binary semaphore, we would probably use it like I'm showing down here. When we declare it, we probably don't have to give it an initial value. It's assumed to start out with a value of 1. When we, I'll try that again. If we used a semaphore like this, we could use it to efficiently implement a solution to the critical section problem. When we declare it, it automatically starts out at 1, and then we could just wrap acquire and release code around any critical section we want, and then we could have a working solution to the critical section problem. It might seem like binary semaphores, since they don't really maintain a count. They're less useful than counting semaphores. I'll admit, they're sometimes a little harder to use, but they are provably equivalent to counting semaphores. If you had a working binary semaphore, you could use it to build a counting semaphore. I'm seeing a lot of questions, I think, popping up in the chat. Does anyone want to ask a question? I can take a look at them, but I'm worried it would distract me from the lecture too much. Any questions anyone wants to ask?
We're mostly able to resolve it ourselves. Thank you.
Okay, I'm hearing a lot of messages arriving on my screen. Are you hearing that? Like that sound right there? Nope.
I don't think we hear it. No, it's
good.
Just you.
I was hoping you didn't hear it, but I was worried that it was irritating that these sounds kept popping up. All right, all right, so I've just made a distinction between counting and binary semaphores. It's worth it to know that binary semaphores are out there, but the ones we're going to use are really counting semaphores. And that's what we're going to depend on for the rest of the semester. What do I mean by really use? Well, so far we've just been writing pseudocode for semaphores, but in both of our implementation languages, Java and C, you can really write code that uses exactly what we've been talking about. So we just need to learn a short API for doing this, and we'll learn it in both of those languages. So POSIX, you already know POSIX provides threads through, among other things, POSIX threads. The POSIX API also defines semaphores that you can use. If you want to use code that uses semaphores, there's a header file, semaphore.h, that you can include. Then whenever you want to make a semaphore, you can just make a variable of this type, sem_t. That's defined in that header file. When you make a variable of this type, I'll mention there are kind of two ways to do it, and it depends on whether you want to use anonymous or named semaphores. I'm going to talk about anonymous ones first. These are for semaphores that you would want to use within a single multi-threaded process. So it's for coordinating the behavior of multiple threads, all inside the same process. And if you wanted to use semaphores like that, you'd make one or more variables of type semt. Before you can, so these two calls down here are the important ones. In fact, let me go ahead to my next slide because it's color coded. So these two middle calls, those are POSIX's name for acquire and release. And I warned you that even though the ideas are always the same for those, the naming varies from system to system. So POSIX, the idea of wait, they call semwait, or sorry, the idea of acquire, they call semwait, and the idea of release, they call sempost. And these two calls, you just pass them the address of a semaphore, and then they either acquire on it or release on it. Before you can use it, you have to initialize a semaphore. Among other things, you've got to give it at least an initial value. And that's what this seminit does. So before you can use a semaphore, you've got to call seminit. You give it the address of the semaphore you want to initialize. You give it a p shared flag, and that's for a behavior of semaphores that we're not really going to use, but that's for saying whether or not the thread is used within a single process or is expected to be used between processes. And this last value out here is its initial value. So if you wanted to write mutual exclusion code and you wanted a semaphore that started out with a value of 1, that's what you put here. When you're done with a semaphore, it might consume some OS resources, kind of like having a file open. So you're expected to call semdestroy to release any of those resources. And here also, it just expects a pointer to the semaphore. I've got an example piece of code that I thought we would take a look at that uses POSIX. Back on my slide, I mentioned there are named and anonymous semaphores. And if you're using these first two red calls, you're working with anonymous semaphores. They don't really have a name. They're just for using within a multi-threaded process. I've got a multi-threaded process. It's called race 6. The reason is I've got a whole collection of programs that exhibit race conditions. I don't usually take the time to show them all because it takes some time in class, but that's why there are a bunch of versions of that sitting out there. This is kind of like that first race condition program we looked at. It's got a volatile int variable val that starts out at 0, and we're going to have threads that are trying to increment and decrement that at the same time. So we're trying to exhibit a race condition. I've got a flag called running that's going to tell my threads when to finish up. I let them run for, I think, 2 seconds, and then I tell them to exit by setting this flag to false. Let's look at the code. So here's one of my threads. It's going to thread 0. As long as so it's got a loop. As long as the running flag is true, it's going to over and over try to increment and then decrement those variables. I changed this a little bit from the first race condition program just because I had to change it to make it work reasonably. But if I'm doing this, either of these instructions, while some other thread is trying to do the same kinds of instructions, we already saw that can leave the variable in unknown state. And there just happens to be another thread down here, thread 1, that's trying to do just that. Over and over, it's trying to increment and decrement them. If we run successfully, well, we both increment and then decrement, so that variable should have a value of 0. But if I didn't have this mutual exclusion code in this program, we would see a race condition, but I added it. So inside, if you think of this as the critical section, then inside, every time I go into the critical section, I do a semwait on a semaphore variable. So this is like an acquire. This is entering the critical section, locking everyone else out. And then on the way out, I do a sempost. So that's a release. And the other thread is doing the same thing. So it's essentially acquiring and then releasing, locking everyone else out. Where did this lock variable come from? Well, I skipped over that up at the top. It's right here. I just declared a lock of type semt. I made it global so each of these threads can see it. And then they just acquire and then release on it around what I'm calling this critical section code. There's one more thing we need to see to make sense of this, and that's down in main. I have to initialize this. So before I start making threads, I do a seminit on that lock. Remember, all of these functions expect the address of a semaphore. If you look up here, when I declared the semaphore, I just made it an object of type semaphore. But then whenever I pass it to any of these functions, I'm passing in its address. So I give it the address of my semaphore. I don't need anything special for p shared, but I want it to start out with a value of 1. And then I make a thread running in each of those functions. I let them run for 2 seconds. So I just wait for 2 seconds and see if they're going to mess up that variable. And then I set the running flag to false. So that's going to force them both to exit. I wait for them both to exit. I don't want to look at that variable before they're done messing with it. So I wait for them to exit. And then I print out the value of that variable. And if we're lucky, it should have a value of 0. Oh, and like I said, I do a sem destroy at the end because I don't need the semaphore anymore. I think that's it. Let's give this a try. I've already compiled it, so we should be ready to run it. And it should take about 2 seconds. And you can see with the mutual exclusion code added, I am always getting a value of 0 for that. Whereas if we went in, we want to try something. Well, I was going to say we could go in and get rid of that mutual exclusion code, and I think then you would see we start having a race condition again in the same program. That's our example of anonymous semaphores. We're using them between multiple threads that are all in the same process. If you need multiple processes that can communicate with each other using semaphores, you can have that too. That's what named semaphores are for. If you're going to use named semaphores, you're going to make and destroy them using these 2 blue functions down here rather than the red ones. But you're still going to use these same 2 middle functions to do the job of acquire and release. So I've got an example of a named semaphore. It comes in 2 parts because I want a semaphore that works between different processes. So we're going to make a named semaphore and then try it out. Any questions before we look at that next example? All right, so this program, it's kind of like those first message passing programs we looked at, except there's not actually a message that gets passed. I'm going to have one process that's going to wait on a semaphore, that's going to acquire on it, and then another one that's going to release on that, and that'll wake up the first process. I called this program tag because I think of it as one process kind of tagging another one. And that's why the process that does the waiting is called tag dest. It's the destination of the tag. It's the one that receives the tag. Here I don't make any threads. I'm just using these 2 processes to coordinate their behavior by using a semaphore. Here's the call to sem open. This is kind of like some other interprocess communication objects. This one lets you say whether or not you want to create a new named semaphore. That's what this flag out here is doing. If this semaphore didn't already exist, I want you to make it. It lets you pick permissions for the semaphore, and this octal number means I can read and write that semaphore, but other users shouldn't be able to. And this first string is a name, kind of like we did this with message queues. They all had names that started with a slash, and the convention for named semaphores is similar. I want to make a semaphore called tag semaphore. Sem open returns a pointer to a semt. Notice when we were using an anonymous semaphore, we just made a value of type semt, and then we passed its address around. Here, since sem open returns a pointer, I just store that in a pointer variable. So the type of my semaphore is different, but that's only because I'm using 2 slightly different calls to work with it. This creates the semaphore. I skipped over this line up here. This is just a paranoia line on my part. Sem unlink destroys a semaphore if it exists. If I run this program and it crashed or something like that, that semaphore might still be out there, known to the OS, but it might have an unknown value. So to try and get a clean start on that semaphore, I delete it, or at least this program deletes it if it already existed, and then goes ahead and makes a new one with an initial value of 0. I think I skipped over this in my slides. But if you look out here, the last parameter to sem open is the initial value for that semaphore. Here, I want this program to wait on the other one, so I'm going to start that semaphore out at 0, and then we're almost done. The next thing I do is I sem wait on that. Notice since my semaphore is already a pointer to a sem_t, I can just pass in a value of that pointer here. I don't have to put an ampersand in front of it. And then I will sit here not consuming any CPU time until some other process does a release on that semaphore, does a post on it. And then once I wake up, I close the semaphore, I unlink it, same call we made at the top that deletes it or tells the OS nobody needs that semaphore anymore. And that's all there is to it. Let's look at the other guy, tag source. This is the one who sends the tag, so I called it tag source. This one says it's not my job to make the semaphore. I'm counting on the other guy doing that. So I'll just open a semaphore with that particular name, and then I'll immediately post on it. That should wake up the other process, the one that was sitting there waiting on that semaphore. And then I close it. I don't unlink it because I made the other program responsible for that. So let's give this a try. I'm going to run tag dest. All right, so at this point, it has made that named semaphore, and it's blocked in semWait in its call to essentially acquire. Down here, I've already got the other guy compiled, and this will happen fast. But when I hit enter here, this program at the bottom will open a semaphore that this one already made. It will post on it, so it'll essentially do a release. That'll wake up this program, and then they'll both exit real fast. I mentioned this is kind of like some of the IPC inter-process communication programs we wrote earlier, but you remember our shared memory program, I made a point of how it was inefficient since it used busy waiting. When the receiver was waiting on a message, it was just wasting CPU time. But not so here. Since the OS has implemented that sem wait for us, this process should be blocked. It's not burning any CPU time, but as soon as we post on this semaphore, it should wake up this process. And like I said, they should both exit really quickly. So this is our POSIX API for working with really two types of semaphores. I made the point that these top calls, these top four, are for working with anonymous semaphores, the ones you would use within a multi-threaded process. And these bottom four are for working with named semaphores, the ones you would use between processes. I mentioned this already. If you're using a Macintosh and you're developing on your Macintosh, so not in a VM or not logged in somewhere, be aware that this API doesn't work. At least last time I checked, it didn't work. It compiles just fine, but things like a sem wait don't actually make your process wait. Apple has chosen not to implement this API. Code that uses it will still compile, but it's not super useful if it doesn't actually do anything. So just be careful if you're accustomed to developing on a Macintosh for this. You'll want to use one of the remote Linux machines, or you could run a VM and develop on that if you wanted. And even if you have a VM running on your Macintosh, these semaphores will still work just fine. They just don't work on the host. Questions before we move on? I mentioned we're going to learn an API for semaphores in each of our implementation languages. And so far we've been talking about C, but Java also has support for semaphores. It didn't have it when it initially came out. This is something they added a little bit later. And I think it's because so many people like myself were just writing their own code to do semaphores. It's not hard to do in Java. And if you're accustomed to thinking like that, it's kind of nice to have access to semaphores. But they've since added it, so we don't have to do that anymore. No surprise, in Java, a semaphore is a class. It's java.util.concurrent.semaphore. So if you have a using clause for that, then you can just start using semaphore just like a regular type. This is the same, I think it's the same package that when we talked about thread pools, that thread pools were also defined in that package. So this is support for a lot of multi-threading things. If you want to make a semaphore, you just construct an instance of this class. So if you wanted to make one with a value of 5, you could just say new semaphore, and you can just pass in a parameter of whatever you want its initial count to be. When I picked the names acquire and release for talking about semaphores, I picked them because that's what Java uses. So here, if you want to acquire on a semaphore, s.acquire will do that. So just like you would expect, that'll block the calling thread until the semaphore has a positive value. .acquire throws interrupted exception. I think we saw that when we were writing threading code to begin with. So if you use .acquire, you're going to have to think about how you want to, it's a checked exception. So you're going to have to think about how you want to structure your exception handling code. I think the example I've got, I just wrap acquire or try and catch around every call to this. There are probably better ways to do that. If you don't want to have to worry about that, there's a version with a slightly longer name, acquire uninterruptibly, that does not throw that exception. If an interrupted exception happens, I think internally it just catches it and tries to acquire again. So if you use this longer method name, you won't have to worry about try catches for these calls. And then the release on a semaphore is s.release. So the same names we've been using so far. I've got an example of Java semaphore code, but we'll talk about that when we start talking about classic synchronization problems. So this is the API we're going to use. It's pretty straightforward. A constructor, and then 3 different methods, and 2 of them do almost the same thing. So I would say just remember that for a moment until we get to classic synchronization problems. And you won't have to wait too long, because the next thing we're going to talk about is more classic synchronization problems. We already talked about one of these. The bounded buffer producer-consumer problem is one of the big 3 classic synchronization problems. I think the intent here is they give you some practice thinking about solving non-trivial synchronization problems. They they show you how to write some code that might actually show up in an implementation that you might do in the future. We are going to look at the usual 3 of them. I mentioned we already saw the bounded buffer producer consumer problem. The next one we're going to look at is the dining philosophers problem. And then kind of probably our last day on synchronization, we're going to talk about the readers writers problem. Let's talk about the dining philosophers problem. This is a silly problem. And when I have to explain it in class, I always feel a little bit silly. But let me describe it to you as if it's not silly. And then I'll tell you what it's really about. So it's a made-up problem. It's a pretend problem, but it does relate to problems you might have to solve in practice. We're going to pretend we have philosophers sitting around a circular table like this picture shows. Here I've got 5 of them, but it could be any number of philosophers. They do what philosophers do, and I'm told philosophers like to go back and forth between 2 things. They like to think, so they like to try to solve problems in their mind, and then eventually they get hungry and they like to eat. So we'll pretend all of our philosophers are always going back and forth between thinking for a little bit and then eating for a little bit. These philosophers are, we'll say they're from a country that uses chopsticks. So to eat, we're going to give them each chopsticks, but we're going to save some money on the chopsticks by buying chopsticks to sit between each of the philosophers. So if you're the philosopher on the bottom, you can still get 2 chopsticks. When you want to eat, you just get the one on your right and the one on your left, and you pick them up and you start eating. So every philosopher has easy access to 2 chopsticks. But they can't all eat at the same time, because if this philosopher at the bottom is eating, this one's going to have to wait. Because even though she can have this chopstick, this one's in use till it gets put down by this philosopher. So that's how this puzzle will work. We want to write a solution where every philosopher gets to go back and forth between thinking and eating, and none of them will literally starve. If one of them wants to think, they will always eventually get a chance to think. Now, I mentioned this problem is a little bit silly, imagining that we're going to save some money on chopsticks like this. What it's really about is processes or threads that might need more than one resource at a time. Depending upon what your program has to do, maybe you've got a process and the next step it needs is to open this file and this file. Maybe the chopsticks are really files. And if you're not careful about how you manage the need for multiple resources, philosophers can interfere with each other. They could effectively make some of them starve for access to resources. So even though, again, we've got a silly story that we're telling with this picture, it's really about processes and threads that might need multiple resources. Any questions about the definition of this problem before we look at a solution? Here's a solution. So this is using, it's just using our pseudocode, but I've got an example of a working version of this solution that we'll look at in a moment. I'm going to pretend that, let's just pretend we have 5 philosophers. So that means we have 5 chopsticks, one sitting between each pair of philosophers. And I'm using our semaphore pseudocode, so I'm pretending we can just declare variables of type sem, and those give us semaphores. And I'm starting those all out with a value of 1. So you can think of that 1 as saying that chopstick is available. Every philosopher, when you make them or when you start running them, you're going to tell them who they are. So you're going to pass them an integer. And so there'll be a philosopher 0, a philosopher 1, all the way up to a philosopher 4. And then while they're running over and over again, they're going to try to think, and then they're going to try to eat. But before they can eat, they have to acquire their 2 chopsticks. So after they're done thinking, philosopher I will grab the chopstick on her right, and philosopher I will grab the chopstick on her left. And then we'll try to eat. And then when that philosopher's done, she'll put down her 2 chopsticks. And then if someone was waiting next to her for a chopstick, now they can have that. So we're just using the plain old semaphore calls that we talked about earlier. This is just pseudocode, but we'll look at a real solution in a moment. What do you think about my solution? I'll give you a hint. It's bad. What could go wrong with this solution?
You're
go ahead.
attempting to acquire 2 specific chopsticks, and some of the ones you aren't trying to acquire might be available, but not the ones you are trying to acquire.
Yeah, so it may underutilize some resources. I don't feel too bad about that, even though you and I know all the chopsticks are identical. And this doesn't permit someone to reach across the table and grab a chopstick. If we were talking about a real problem, a real programming problem, usually you would want particular resources. So if you needed 2 particular files to do something, then you need those files. So even though chopstick is a little silly here, we'll pretend that if you want 2 chopsticks, you want the particular ones on either side of you. Anybody else? Problems with this solution?
One philosopher could eat forever, and it would stop the philosophers on either side of them from ever eating.
That's a good point, which I'm also not prepared to address. I guess I'm assuming once a philosopher starts eating, they will eventually finish eating. There may always be some philosophers eating and some who aren't, but no philosopher eats forever. And I probably should have said that earlier. What I think, so those are all things that we could think about for added concurrency. But I think the real problem, at least the one I planned for this solution, is if every philosopher picks up the chopstick on their right and then picks up the chopstick on their left, it's possible that they could all get stuck holding, it seems unlikely, but it's possible that every philosopher could first pick up the chopstick on their right. And if they all did that at about the same time, and then they turned to the left and tried to pick it up, they would all see that their left-hand chopstick is taken, and they would be stuck there forever. Nobody's eating. Everybody has gotten past this line of code, but they're all stuck in their next acquire because they can't have the chopstick on the other side. So that's what I planned here. This solution could deadlock. And we talked about how that could happen. And it may seem unlikely. You could say, how likely is it that they all pick up their right-hand chopstick and then go to pick up their left-hand chopstick? I wrote a simulation to try this out. And this is what I had in mind. Remember I said, we'll look at the Java API for semaphores, and here's a program that uses it. So this is a working Java program that simulates the dining philosophers problem. Up here, I pick how many philosophers I want. I'll have 9 of them. I'm going to make a semaphore. This is that same class that we just looked at, and you can see I think I said using a moment ago because my Java's rusty, but I import the semaphore class. So I've got an array with a slot for 5 semaphores. Let's go ahead and look at the code for a philosopher. So each philosopher is a subclass of runnable. They all have a rank, so that's just their number, philosopher 0, philosopher 1. When I construct them, I tell them their rank, and then they just remember that in this field. And then here's their run method. So they don't run forever, but here's what every philosopher does for 10,000 iterations. They report that they're thinking. So philosopher 0 is thinking, philosopher 1 is thinking. And then once they're done thinking, so that's, I'm pretending they're thinking there. And then they're gonna eat. They print out a message that they're eating, but before they do, they acquire a semaphore on their right and then a semaphore on their left. So whatever their rank is, and their rank plus 1 with mod by n to wrap around. And then they print out that they're eating, and then they release their 2 chopsticks, and they just do that 10,000 times. Notice I'm using that acquire uninterruptedly here, so I don't have to worry about try-catch code in this. Down in, well, this is sort of main, it's just another method. It's an instance method that I call from main. I've got an array with a space for 5 semaphores, but all those are null references until I make them refer to semaphores. So I make 5 semaphores, each starting out with a value of 1. Then I'm going to make my n philosophers. I make an array with a slot for each philosopher. I make a new thread for each philosopher, and I pass them, this is that runnable class we were looking at before. So this is what they're going to do when they run. And remember in Java, making a thread doesn't start it running, but I can call .start as I make them, and then they each start running once I've made them. And then they'll take however long it takes to run 10,000 iterations, and then I'm just going to join with each of them. So I go through my array of philosophers, joining with each, and then I think I'm done. Yeah, this is just main that calls that other method. So any questions about this? This is your first example of using semaphores in Java, and the interesting parts are for semaphores are right here. Here's where I'm making each of my semaphores and giving them an initial value, and I make 5 of them. And then, like I said, up here, these are the calls to acquire and release with the same terminology we've been using. All right, I think this is already compiled. Let's give it a try. Java dining philosophers. And you can see it was off to a good start. A bunch of messages scrolled up, but now we're not getting any messages before. And I think it's that reason we were talking about. I think this program deadlocked. I think we're in that case where every philosopher has grabbed the chopstick on their right hand, but they're waiting for the chopstick on their left hand. Let's give it another try. Well, a different sequence of things happened, but it looks like we're deadlocked again. Looks like we're deadlocked pretty fast there. So this is my answer to this question up here. But really, what are the chances of this actually deadlocking? And we saw that for this particular program, it seems like it's deadlocking every time we run it. We ought to be able to fix this. And we've got a whole chapter that we spend, I believe it's chapter 8. Yeah, chapter 8, talking about the problem of deadlock. and different approaches you can have to dealing with that problem. We can make up our own solutions here. If we bought one extra chopstick, so at the end, let's say the table was not circular, but it was in a line, and everyone had 2 chopsticks on either side. Well, if we could put those philosophers in a line rather than having be circular, then that one extra chopstick at the end of the line would keep us from getting in a loop all waiting on each other. So that seems like it could help. How about this? Only one of them at a time can eat. That'd be even easier to implement. Instead of having a semaphore for each of your chopsticks, we could just have one big semaphore. And if you wanted to eat, you could acquire on that. And then when you're done eating, you release on it. And since you know that only one person can be eating at a time, if everyone's going to acquire on that semaphore before we eat, then once you've acquired on it, you know you can have your 2 chopsticks. You don't even have to model them separately. Disadvantages with that, anybody? One at a time can eat?
It kind of ruins the point of multi-threaded processes.
At least for the eating part. They can still think concurrently, but I agree with you. It would reduce concurrency. And if you've got 5 perfectly good chopsticks around the table, you could hope that often at least 2 philosophers could eat. So yeah, that seems like, even though it's easier to implement, it hurts concurrency. So I'd say that's a bad solution. How about this? You can only pick up your chopstick if you can have both of them. So this is kind of like those atomic instructions I was talking about. When you want to eat, you real fast, look at the chopstick on your right, look at your chopstick on your left. And if you can't have both of them, you don't pick up either of them. But if they're both free, you pick up both of them. Well, I went back to the picture here because there's a hazard there. Let's say you're this philosopher and you want to eat, and the philosopher to your right is eating. Well, you can't eat, so you have to wait. But let's say before your philosopher to the right finishes eating, the one on the left starts eating. And then after that, the one on the right stops eating. Well, you still can't eat. And let's say before the one on your left finishes eating, the one on the right resumes eating, and then the one on the left finishes. Even if they're all eating for a while and thinking for a while. So sometimes they're not eating. These 2 philosophers, especially if they were your enemies, they could starve a philosopher in the middle just by making sure one of them was always eating. So acquiring all of your resources at once seems like it could prevent the deadlock, but it seems like it could also cause starvation for philosophers. And we'll see an example of that. And this last one is kind of like the first one we talked about. Well, actually, I take that back. There's another way of doing this. We could break the symmetry of the problem. What I mean is every philosopher around our table picks up their chopstick on their right, and then they pick up the chopstick on their left, which means they can get stuck in that situation where they're all stupidly holding their right-hand chopstick, waiting on their left one that's never going to be available. But what if we had one left-handed philosopher? One who did things the other way. One philosopher who picked up their left-hand chopstick first and then their right one. That would be enough to keep this from happening. That would be enough to make sure, because of that one philosopher doing things differently, that would be enough to make sure this never happened. And I got a version of the program that does that. It's called Hunger Games. It's almost the same code, so we can go through it real fast. We still have 5 philosophers. Every philosopher knows their rank. But when they get ready to eat, we're going to have one philosopher who does it differently. Most of the philosophers are going to do this. You can think of this down here as picking up your right-hand chopstick, then your left. But if you're the last philosopher, if your rank is 1 less than n, so philosopher number 4 if we have 5 philosophers, you're going to pick up your left-hand chopstick first, and then your right one. And everything else in this program is the same. Even the order they put down the chopsticks is the same. But I think this is going to be enough to prevent our deadlock. Let's give it a try. And you can see this time, at least this version of the program, seems like it's making it all the way through. Well, technically we have 1 more minute of class, but I'm going to say that gets us about to the end of our time. This is where we'll pick up next time. So we've still got a few problems to talk about with synchronization, and this potential for deadlock is one of our problems. I'll stop the recording now, but if people want to hang around and ask questions, I'll be happy to give them a try. Otherwise, I'll see you on Monday. Good luck on your exam if you haven't finished it, and good luck on your project that's due on, or your homework that's due on Monday evening.